Alright, so the next topic that we're going to discuss is simple harmonic motion. So that's where we'll head next. And so first, let's talk about simple harmonic oscillators, which are basically objects that undergo simple harmonic motion. And then we'll see that there's basically two types that we'll talk about. The first are objects that bounce back and forth. And so this is like our spring and mass system. So if I pull the spring out, and here's a situation where, you know, problems up until now, we haven't attached the spring to the mass, or we've given it a chance to come off in certain situations. So here's just a situation where we're going to let it stay attached to the spring and it'll bounce back and forth. And it bounces back and forth because there's a restoring force that's trying to return the system to equilibrium. So again, equilibrium we know is the point where the forces all balance out. It's the point where the spring force is zero, and the restoring force is always trying to get the system back to equilibrium. The other type of simple harmonic oscillators we'll have are ones that swing back and forth. And so the example we'll deal with is the simple pendulum. So basically, if I take a string, put a mass on the end of it, and let that swing back and forth, I've got a simple pendulum. And then with a simple pendulum, or any of our oscillators that swing back and forth, what I've got is I've got a restoring torque that's trying to return the system to equilibrium. So for our pendulum, equilibrium basically means straight up and down, right? So where does it come to rest? If you let it run and come to a stop, it's going to come and stop straight up and down. And so that's the equilibrium. And so when you pull it away from straight up and down, there's a restoring torque. So anytime you have a restoring force or a restoring torque, you end up with simple harmonic motion. So simple harmonic motion is sinusoidal motion, which basically means that when you let this object bounce back and forth, you're going to get a sine curve. And so what we've got here is we've got displacement, right? So how far it is away from equilibrium as a function of time. Again, the amplitude is the name we give to the maximum displacement, and the period is a length of time that corresponds for how long it takes to go all the way through one cycle. So just like with circular motion we talked about a period, simple harmonic motion also goes through a period. So it will return to, say, maximum positive amplitude in one period. Since we've got a sinusoidal motion, we have an equation that describes that, and in this case what we're going to do is we're going to use a cosine curve. So we're going to have, for our simple harmonic oscillator that's bouncing back and forth, it'll be x is some displacement from equilibrium. X as a function of time is given by the amplitude, that'll be the maximum displacement, times cosine, and this is all known as the phase. So omega t plus phi is the phase. Phi over here is the phase shift. It basically just says, it gives us the ability to start our clock when we don't have our mass out at amplitude. But what we're typically going to do is we're going to pull our mass out to its maximum displacement and then let it go, and we'll start our clock when we let it go, and so that therefore our phase shift will be 0. And so we'll deal with the equation A cosine omega t. Omega, we've seen up till now, we've dealt with omega as the angular velocity. Well, here it means something a little bit different. It means the angular frequency. And so we're going to take omega and multiply it times t, and this still has units of radians per second. And so when we multiply it by seconds, we get something in radians that we can plug into our cosine curve. So again, the subtlety here is we've used omega as the angular speed or angular velocity. Now it means the angular frequency, and it's just giving us a sense of how fast our system oscillates. So we want to be able to relate the period to the frequency and the angular frequency. And so period, again, that's big T, that's the time to complete one cycle. It's going to have units of seconds. The frequency, that's little f, that's the number of cycles per second. that has units of 1/seconds. That's also called a hertz. So when you see things in units of hertz, they're telling you the frequency. Omega is the angular frequency. And so that's, again, telling us how fast our simple harmonic oscillator bounces back and forth. And it still has units of radians per second. Now, all these things relate to each other, right? The period is 1 the frequency, and it's 2 pi over the angular frequency. And you can just rearrange this equation for any of the parameters that you want here. So if you want the frequency, that's 1 the period, or it's omega, where we're dividing out the radians, so divided by 2 pi. Or the angular frequency is 2 pi over the period, or it's 2 pi times the frequency. So these are really just, basically it's the same two equations, we've just rearranged them for whichever variable we're interested in solving for. So this is how the period frequency and angular frequency all relate to each other. So we said we've got an equation of motion that gives us the position, right? Our displacement from equilibrium is a function of time. Well, the way this works is that I can figure out the velocity and the acceleration also as functions of time, and those are also sinusoidal curves. So I've got a cosine curve, then a sine curve, then a cosine curve. And so what you notice is, with the velocity curve, I've got an extra omega tucked out in front here with the amplitude. With the acceleration, I've got an omega squared tucked out here with the amplitude. And a cosine omega t plus phi is really just another way of saying the displacement. So one way to define simple harmonic motion is that it's motion that follows the pattern that the acceleration is equal to the negative sign is our restoring part. I've got a constant, right? Omega squared just ends up being some value times the displacement. So the farther you pull it away, the larger the acceleration is going to try and restore it back to equilibrium. Now, if I'm interested in the maximum displacement, well, cosine and sine curves, their maximum value is just 1. So the maximum displacement, that's just my amplitude. The maximum speed, so I'm not worried about sine here, but the maximum speed is just going to be omega times the amplitude. The maximum acceleration is omega squared times the amplitude. So basically, the maximum value for each of these parameters is just what's the number out in front of my sine or cosine curve. And so we'll be able to use these to calculate how far, what's the maximum displacement, maximum speed, maximum acceleration that our simple harmonic oscillator feels. So if I take these curves and plot them, right, there are a couple things to sort of pay attention to. So here, displacement's the blue curve. So here's my object as it bounces back and forth. Velocity's the red curve. Acceleration's the green curve. There's nothing particularly special about the heights of each of these curves, but there is something special about how they sort of relate to each other in time. And so if I pick a particular point in time here, and I'll happen to pick where my object is at its maximum positive amplitude. So here's my box, right, my mass attached to the spring for my spring and mass system. Initially, at this point in time, it's at maximum positive amplitude, because I'm saying to the right's the positive x direction. Well, what you notice here is that the velocity curve is 0, and the acceleration curve is negative. And it's also at its maximum. And so what's happening is that when my mass is out here at an amplitude value, it has to stop to turn around, and the acceleration is as large as it's ever going to get, pulling it back towards equilibrium. If I wait 1/4 of the way through the period, then I'll notice that I'm back at amplitude, or I'm back at equilibrium. So here's a situation where my displacement curve is at 0. The acceleration is 0 because equilibrium is where I feel no force, so I don't have any acceleration. But you notice that my object is now traveling at its maximum speed. In this case, it happens to be traveling with its maximum speed in the negative direction because it's moving back to the left. I wait another quarter of a period, so now I'm halfway through the period, and now I'm over at negative amplitude. So my box has gone from positive amplitude to negative amplitude, and so now it's at its maximum negative displacement. The velocity, again, is 0, and the acceleration is now at its maximum value but pointed in the positive direction. Let it bounce back to equilibrium, and again, now its displacement is 0. It's moving with its maximum speed, but now in the positive direction, and again, it feels no acceleration. Let it go one more time, and now it's back at, I've completed the period. So part of what you notice here is that the acceleration and the velocity always point in opposite directions. When one's positive, the other is negative. They're both 0 at the same time. And then the velocity is always 0 when the displacement and acceleration are at their maximum. And the velocity is at its maximum when the acceleration and displacement are 0. So this just corresponds to my object stops at amplitude and it's moving its fastest at equilibrium. So the two systems that we're going to deal with, we said, are the spring and mass system and the simple pendulum. And so basically what we'll see is that the angular frequency for a spring and mass system is defined by how stiff is your spring, that's our spring constant, and what mass have you attached to the end of it. And so the angular frequency for our spring and mass system is just the square root of spring constant divided by mass. To get the period of our spring and mass system, well, period t is just going to be 2 pi over omega, and so that's 2 pi divided by that fraction, so I end up flipping it over, so it becomes 2 pi times the square root of mass over the spring constant. So if I know what k is and I know what m are, so I know the spring constant and I know the mass, it's simple enough to calculate the angular frequency. That's going to tell me the rate of oscillations, and then it's easy enough to calculate the period. That's just 2 pi over the angular frequency. The other simple harmonic oscillator that we'll deal with is the simple pendulum. And what defines a simple pendulum is basically if I can act as if all the mass is located at the end. So I can think of this as a massless string, and then all the mass is down here in what's known as the bob. And so again, I can calculate the angular frequency of a simple pendulum. That's just going to be the square root of g over L, where g is my gravitational acceleration and L is the length of the string. So the first thing that you should notice is the angular frequency for my simple pendulum doesn't depend on what mass I have. So if I can act like all the mass is at my end of the string, then I don't actually care how much mass there is. It's not going to affect the angular frequency of my simple pendulum. Right, so it does not depend on mass. Now I can calculate the period of my simple pendulum by just taking 2 pi over the angular frequency, and again my fraction flips over underneath the square root, so this is 2 pi times the square root of L over G. So what we'll do is we'll use these equations, we'll pay particular attention to sort of where within the cycle it is, how far has it gone a quarter of the way through the period, halfway through the period, all the way through the period, to figure out what's going on with my object. And then I'll know from these parameters, right, the gravitational acceleration and the length of my string with the simple pendulum, the spring constant and the mass with the spring and mass system, I can figure out what the angular frequency is and therefore what the period of my motion is going to be.